Hello, everyone. Thank you for joining us on this session on cost effectiveness, harnessing state-of-the-art technology to scale viable carbon farming MRV. This session is based on contributions from 5 propositions to the summit, and we tried to provide you something coherent and an overview of different technologies that could be of interest here for the subject. And the session will be divided into 2 parts. So first, I will speak about the objectives, a reminder of the objective. So the objective is to move beyond the cost accuracy bottleneck to deploy a new generation of technological tools, optimize uncertainty and drive down the cost per credit, ensuring commercial viability under CRCF. We try to show this through different presentations with real case applications from Italy, France, North America, with different technologies also. And also how the data is being manipulated, a presentation from Italy on optimal sampling strategies. And also there is a discussion at the end on systemic barriers for maturity of solutions, of the solutions that are being discussed here, and data accessibility. So your interaction will be important here so that we can get really very useful recommendation, because after each session we need to make recommendation. So please don't hesitate to contribute during the Q&A. So the session is divided into 2 parts. The first one is technical showcase of the tools viable. It's 4 presentation, 10 minutes, 2 minutes questions, and then an interactive panel at the end, moderated by Stuart Gee from Climate Kick on the scaling through public data and tools integration. So I'll just present myself now. I lost my presentation, but I can still present myself. Ahmed Al-Bitar. I am head of development of AgriCarbon.io, which is an MRV tool that we're developing at CESBio CNRS. I'm also a researcher in remote sensing and integration of remote sensing data into modeling. So we've been contributing to different projects for Orkaza, Marvik, and Kafamor. And I will leave the place here for the first presentation by Helen. Yeah, I think the first presentation is the one by Helen. Maybe we can start the presentation by Helen. Is she here? Yeah, here we go. And then my presentation will be after. Please, Helen, present yourself.
Hi, everybody. Just to confuse everybody, I'm Helena Black from AgriCarbon, which is nothing to do with AgriCarbon.io. AgriCarbon is a relatively small direct measurement company based in Scotland, but with labs in UK and USA. And I'm here really to talk to you a little bit about our journey to improving direct measurement using technology innovation and how important that is in understanding the role of technology innovation in driving down errors and cost, but equally the limitations to that in terms of direct measurement. And I should say here that obviously I'm chief scientist at AgriCarbon, but I'm also a research fellow at the James Hutton, where I used to be based when the seeds of AgriCarbon were formed, and partaking in Kafamor to deal with some of these issues to do with how do we measure soil carbon stock change. And on the right hand side you see some of our sampling kit. I'm going to set the scene, and I apologise because I've got to read what I've written because I wrote this quite late last night, really to set the context of what do we mean by uncertainty. Now, to some of you, I apologise, this will be granny sucking eggs, as we say back in UK, but uncertainty is a critical factor when trying to understand the cost, the risk, and the value of any part of soil carbon MRV. And we've realised in our journey that that is almost like the critical endpoint, that we need to understand the contribution that direct measurement makes to the uncertainty reporting or deductions, particularly in voluntary carbon market credits. Uncertainty deductions in model and measure can be typically 30% of the value of your credit. And it's not just error, as I'm about to demonstrate. I'm going to set the context, and this is purely to say how have we come to this idea. So AgriCarbon has sampled all of these different things. The thing we've come to learn from a direct measurement company is most people are carrying out MRV using model measure. So we need to understand the role of direct measurement in model and measure quantification as opposed to measure, remeasure, because that's what most projects are about. And we now have an awful lot of data by which we can do various different simulations. And I'm going to show you a few examples of those to set my context of uncertainty and the role of it. I want to start, though, with technology innovation. When the engineers in AgriCarbon told me how they wanted to analyse and improve soil carbon analysis, I honestly thought they lost their mind. Now, this is AgriCarbon's end-to-end service, and what I wanted to really emphasise, each stage in that is where technology is innovating, not just in AgriCarbon, but many companies here are innovating the technology associated with different aspects of design, collection, lab analysis, and the data interpretation, etc. I'm just going to focus on one bit, just to illustrate where I think innovation and more innovation is needed to help us reduce the cost and increase the value of what is being reported. And that is the lab. Automated soil carbon analysis, affectionately known as the ASCA lab, of which there are now 3, is literally turned soil carbon stock analysis into a factory analysis. It is like no soil lab you have ever been in. I have people that now are, shocked by with it when they see it. It's got robotics, it's got automation, and it's got an immense amount of the imagination of the engineers involved on a continual basis. What has it done? It's allowed us, you see the left-hand side, the soil core coming into the lab. That soil core can be analysed in as many different samples as you want, down to a depth of 1 metre. It automatically cuts that core and it will measure SOC, I'll say bulk density, but really we're after soil mass on every single sample. And it does it according to UCAS accredited methods, but it just maybe doesn't do it in the way you think. But what it's critically done is turned it into a cost-efficient, rapid analysis, which brings the cost down. So it'll do 1,000 samples a day, minimum. Each lab will do 1,000 a day. It's reduced the time to report analysis. I don't know how many of you have sat there waiting months for your data to come, but, turn it around in a few weeks. And it's reduced the cost. And it's reduced the cost of this combined SOC, bulk density, mass, by about 80% compared to what we were traditionally having to pay or charge. And that's the critical thing, bringing the cost down. We're also doing it by reducing analytical error. And I can explain to you, we can go into the questions how we've done that, but I wanted to illustrate this from a recent WEPAL test, which many of you may be aware, there's inter-laboratory trials, labs take part in that to demonstrate how good they're doing with the soil analysis, but equally to learn where they may need to improve. And of course, I picked a really good one. We're not always in the middle, right? I admit it, but this is a recent one for us in the middle. And the narrower the bars, the smaller your errors. Typically, the error on an SOC analysis is about 2%. And you see here, the average for the EU is about 12%, right? So we've drastically reduced the error. And I'll come on to why that's important in a minute. But I just wanted to pass on that there's nothing equivalent for bulk density yet. That's a bit of our CAFAMOR project. But we do need to keep that in mind when we're trying to reduce cost, error, and efficiency, because that's a critical part of the equation. What does it really mean about reducing error? Reducing error reduces cost because it reduces the number of samples you need to take in the field. So I've illustrated this by saying, and bear in mind the error here is a compound error of sampling everything else. 250 cores in a farm with 250 cores on a farm will give you a margin error of 1.7 tons using our methodology. If you do it using standard labs, you need nearly double the amount of cores, right? We've got to use technology to get these sorts of efficiencies, particularly at scale. And this is just a way of saying, look, guys, if we can do it, why can't everybody else, right? the last part of it, uncertainty deductions, coming full circle here. This is an example from a project. We've done a bit of simulation. It's a 2,000 hectare project. It's saying that it's going to have a removals of 2.5 tonnes per hectare. The unit price of CO2 is about 50 tonnes. This is illustrative. The bars are the cost of the project from the uncertainty deductions. The blue line is the number of samples you need. Now, effectively, they're the same curve, but I've just put the two on to illustrate my point. The light blue arrow is the point at which no more samples from the field will improve the uncertainty in a model and measure approach. So we know there's a limit to how much we can improve efficiency and increase the sample number for the uncertainty deductions. So it's not all about always take as many samples as possible. It's about how it translates into, is it worthwhile doing it? If your model prediction error, are you around, Guy? There's my trick question. If your model prediction error is actually dominating your uncertainty deductions. So those of us involved in direct measurement, this is a critical thing to understand, is that relationship between model prediction error and sampling error. And we think we've got to the point we understand it well, and we can help to inform our projects to be more efficient. But I have a take-home message for this, and I think I've mentioned this already. If we only take the 660 samples that are required to run the model and are the optimum for the uncertainty deduction as it currently stands, and that is approximately 200 cores less than what we would take if we wanted to have confidence, high degree of confidence in the outcomes. How are we going to improve the model prediction error if we don't have measurement of change in regenerative farming? I shall leave you that question.
Thank you, Helena. Maybe you have time for one question for Helena. Everyone is surprised. So many reduction of uncertainty. Oh, we have one. Let's go.
Thank you. Can we buy your labs?
They sit in a porta cabin. So they're not only scaled, they're not only scaled for in the lab, they're also scaled to fit in a porta cabin so they can be shipped anywhere around the world. So this amazing thinking coming. Yeah. I wish. Yeah. Especially when we talk about seed clay soil like in northern Italy. Yeah. How do you account for that? Really, really good question. So, 3 answers. First one is, that's a specific question we're tackling in Caffamore with Tunin University. So sampling 10 fields every month over the next 2 years to start to look at the dynamics of mass and bulk density. First answer. Second answer, we apply an algorithm. So we measure the cores in the field. We measure the hole in the field. We measure them when they get back to the lab. And we apply a correction factor, an algorithm, that then allows you to cut the core to compensate for the compression. It's not perfect, but it's better than nothing. Third answer, equivalent soil mass. But please don't ask me any more about that today.
Maybe we have a session of discussion. Maybe you can also, if you have time, so that we don't run too much late on time. So maybe we can go to the next presentation, which I will be presenting in this case. Yes. Thank you. So what I will be presenting is the transitioning from long-term farm level to plot scale crop cycles, MRVs, so that we can ensure reliable and consistent quantification of stock changes. So just to put in context, there are different contexts in which we want to do an MRV. Is it for national, for voluntary carbon market, which is the interest of the summit, more connect to the summit, agriculture and environmental policies. And clearly there are different methodologies. We saw Helena presenting the measure-remeasure approach. There's also soil modeling approaches. But what I will be mentioning is the approach we call ecosystem modeling. And it's mentioned at these keywords in the CRCF latest version directive. So it's about crop modeling that produces biomass that goes into the soil. For sure, here there are inputs that can be by crop modeling, but here we'll use also remote sensing. This is a figure from a paper that has been published last week by our team, by Ainoa Yasusta, and it's also on the cookbook for Orkaza. And this is, the figure shows what are the connection in a ecosystem model that is also constrained by Earth observation when available. And next to each of the source of information, there is a graph, there is a arrow for cost and accuracy. And for sure, as we go for more precise information, it's more costly, but we have more accuracy. And what is the right balance between all these information? And for sure, also using soil data, even though we are not doing measure-remeasure, but soil is constraining the system. So we need this kind of information coming in. I will concentrate in my presentation on the Earth observation component because there are so many aspects here. We cannot mention them all. So what we did is we combined Earth observation from satellite at intraplot scale, combined with parsimonious models, which are simple models that we can constrain using the observation from satellite, either crop model or soil models, and also Bayesian assimilation, which is a methodology for informing the model by the remote sensing, while also producing uncertainties. So it's a very good framework to get uncertainties. And our solution is AgriCarbon.io, ICO, and these aspects I'm presenting will be based on this tool. So this is an application over whole France at 10-meter resolution. So it's scalable solution also, which is important in this kind of exercises, because we're going to intraplot scale. We need to demonstrate that it's easy to apply at national scale. And what you see here is a production of wheat biomass over fields, and yeah, it is heterogeneous. And at the same time, this is what's going into the soil. So by definition, by hypothesis of the CRCF or the carbon monitoring, this is what's going to the soil. So this is generating the heterogeneity and the differentiation. So we argue that we also need intraplot scale information. One other reason we need to do it this way is that farmers change the perimeter of their plots across cycles. And we always think, okay, we have a plot, we have a project, we follow them. But actually, the farmer can decide, I don't want this part of my plot. So if you do it only plot scale, actually, and then the next year you need to redo the exercise, actually you lost the information, you need to redo it from zero. So doing intraplot, you can actually manage this modification across the cycle, which is very important. And this is an insetting project that has been running from some years now, where farmers are being given subsidies from Nathaïs, which is first producer of popcorn maize in France. And what you see here is from the farmer's plot, the production, actually, the distribution, histogram of the biomass across the years. And this is changing drastically. So if you're using just a model without any remote sensing, you are not capturing this variability. And this is actually driving all our system. This is the hypothesis of our exercise. So we argue that we need something to constrain. So also, when we do the exercise for carbon, now for the carbon stock, at regional scale, at 10-meter resolution, there are so many pathways and more heterogeneity across the pixels that are there. And this will impact your baseline, but also impact your delta SOC estimates. So this is why you need actually to take into consideration this heterogeneity. But is it cost effective? So this is an example here where actually we are using the planet data. Planet data is daily data at 4-meter resolution, and Sentinel-2 is free data from ESA at 10-meter resolution. And we see that during cover crop periods, we don't have so much of the data from Sentinel-2, and this is a short cycle. So Planet can come in and enhance. So what we're saying here that when you use high temporal frequency information and harmonized data sources, we increase the data input. When you increase the data input, you don't increase the uncertainty because this is constraining your model. You decrease the uncertainty by using remote sensing. And then you decrease the uncertainty and you enhance the uncertainty for SOC estimate. This is the uncertainty decrease as we're using the data from Sentinel-2, Planet alone, and Planet and Sentinel-2 homogenized, because if you use them just directly without homogenization, it can have a bad impact. So we need to homogenize, and the uncertainty goes down. So here the axis is the uncertainty, actually, yield uncertainty. And it's the same proportion for biomass uncertainty. This is another exercise that we've done with Airbus. So Airbus has a very large data set for remote sensing. They have own tools also to produce information from remote sensing. So one of the exercises we've done with them is that we combined, okay, let's go Sentinel-2, Landsat, all Landsat, Spot, which is 4-meter resolution, and Pleiad, which is 30 centimeter. It is here downgraded to 4 meters. And now we have so much more information, and this is extremely important. Why? Because then we can access cover crops, which are the main practice that actually increasing the soil carbon, right? So we need to have a more confidence in the biomass that's producing. And this is not something that the farmer is declaring because it doesn't have the yield. So we need to measure it on the ground. And measuring on the ground is actually quite expensive. So using remote sensing and high density, then you can address a new type of cover crops, like for us, in our case, like mustard, like white radish, and this is facili, it's just a copy-paste here. So this area here, what we looked at with Airbus, is in Bretagne, which is one of the more cloudiest areas in France. So then the density of information is coming in good. So we'll continue this exercise in the CAFAMAR project to advance it more. We're working also with AgroSolutions and SMAG to combine it to their FMIS and more information to get something more reliable. But the message here is that we need more densified information to get more reliable. So I will end with this slide here. So what the message take home here is that combining remote sensing, crop modeling, and soil modeling, which is called ecosystem modeling in the case of CRCF, provides a reliable, cost-effective solution for MRV for SOC because we can scale the solution. We can also adapt this changing perimeter of the plots, and we can cover more and more of the practices that are the most essential for carbon farming. And we know everyone that the most essential one is, in the case of arable lands, is intermediate cover crops, right? Thank you very much, and please, if you have questions.
Is your model compatible or maybe modifiable for permanent grasslands?
Yes, it is compatible, and the word modifiable is good because this means we need a little bit of work on it. We have some exercises we've done in Finland with ICOS sites where, we were capable of getting the right estimate. The issue that we need to work on is that perennial prairies where they have different cuts. So it's quite a technical issue. And what's nice is that last year and the year before, European scale data sets came out on detection of cuts using Sentinel-1 and Sentinel-2 data. So some data coming in that will help a lot of this, for this. Do you have another question?
So first, thanks for the presentation. So you mentioned 3 different approaches at the beginning, notably using a model without crop modeling and with crop modeling. Have you some results about the uncertainty of not using crop modeling versus using crop modeling with satellite images on the final SOC estimation?
Yes, we have an estimate, and one of the graphs I showed was showing the productivity in maize, for example, across. So you're saying about with and without crop modeling? Okay. In the case where you're not using crop modeling, you're using the declaration from the farmer or the regional statistics. And as I showed in the graph, that productivity is quite different, not only per plot, but intra-plot. So the declarations also by the farmer in many cases regroups many plots, but he's not doing the practice everywhere. So it's not like reliable in terms of doing the exercise. So what we're saying here, the cost is not expensive in adding these approaches, but the added value is quite important. Yeah. So thank you for the questions. We'll go to the next presentations. I forgot the order. Maybe you can have the first slide. It's you, I think, yeah. Andrea Ferralini, do you give the, you have the presentation, right?
Check. Yeah.
Yes, great.
Thank you so much, Ahmad. Good morning to everybody. I'm Andrea Ferrarini from Catholic University, and I'm going to present, thanks for Elani and Ahmad to introducing some of the topics that I will address. So the sampling error and uncertainty, and also the added value of remote sensing on many of the MRV operation that a project developer on an MRV provider will face. I'm from Catholic University, and also thanks to Michele Crosi, because most of the credits for this presentation and for the work behind goes to him. And today I want to present a validation exercise of smart soil sampling strategies that we did within the MRV project, but especially in an operational carbon farming project in the northern Italy around the Piacenza province. So the question that we are going to answer is how much and where should we sample? Is even before the error of analysis. So basically, we are in front of 1,000 hectares, for example, and we don't know where to go to sample. So is the sampling paradox? So this is the question that we face. This is just an image of our landscape in Piacenza, where we have many crops, many soil types. So this is the so-called sampling paradox. So on one end, we have such an extreme complexity, many soil types, crop rotations, and even different level of soil texture and soil organic carbon to cover, to initialize our soil carbon models. But on the other end, we are hit by reality. So going around the landscape, unless you have such an operational strategy as AgriCarbon has, in general, there are not so many companies, even the MRV providers, that are logistically ready and market ready to use their technologies, because basically we are logistically constrained. Simply, we have wheat fields where we cannot access this year. So we would like to sample, but we cannot. And basically is time consuming and very costly. So the sampling paradox is that if we do sample too less or at random, our MRV estimates, our SOC removal, carbon removal units at the end of the 5 years crediting period are biased. So under, let's say, and we address the problem of credibility and even certificate issuance. So the question is this one. So this is the kind of reality that we have different type of soil that we have to cover on our sampling strategy. So, and this is the situation of our carbon farming project. Our 8 farms, almost 2,000 hectares, and these are homogeneous and heterogeneous farms because they are not grouped like these farms. They can be scattered with different crops and with different soil types. For example, we have 5 soil types, and this is just 60 kilometers, okay? It's not like even a European scale project. We have 4 soil textural classes to take into account. or even this is the kind of range of clay that we can have. This is quite a heterogeneous landscape. And so concentration, we go from 0.5 up to 2.5%. So this is really hard to handle. So for this, with the MRV project, we have developed an operational strategy, a kind of replicable remote sensing based analytical framework to validate which is the best smart soil sampling strategy. We apply it, and I'm going to show the results to this project that you just saw. And the key objective is quite long, but it's super important because once we identify the best sampling strategy in terms of best combination of sampling unit, pixel base, field base, for example, or predictors, which type of bands, which type of remote sensing products we can use, and which are the best sampling algorithm. Altogether can be found, yes, but which is the best cost accuracy and uncertainty trade-off? Because if we do have too much uncertainty, even if we are accurate at low cost, we can have a huge sampling error that can be propagated in all the fields that we run the models. And especially, we want to initialize our soil carbon model. And we know how much important it is to get the right baseline carbon stock. Because if we do use 60 tons instead of 70, and the previous history, thanks to the tool like the AgriCarbon EO, our tool Remote C, we cannot initialize under steady state, no, at all. So we need to initialize with a spin down, spin up process that really get the real historical carbon inputs. And this is super important for many, many different reasons. So we need to start good. And I kindly ask to the operator, Carlo, if he can click the Prezi link, so we can go and I can show you how we build up the analytical framework, so you understand the reason behind the results that we are going to see. Se puoi gentilmente, Carlo, grazie. Se puoi metterla a tutto schermo, grazie. So, where we start? From a reference dataset. So, we sample everywhere, okay? This is not an exercise that you can do every time. Even if you have a large-scale data set, for example, as we have in Emilia-Romagna region, thanks to the Emilia-Romagna region, we could have access to 60,000 points. So we can do this exercise. But we want, thanks to the help also of the Pioneer Corteva team, we sample everywhere with an intensity of almost 1 sample per hectare. So around all the 700 hectares that you saw before, we sample everywhere. And this is our reference. Then and this is the type of sample that we collect. Then the spatial unit, the predictors. So we combine different type of predictors. So Sentinel bare soil images from Sentinel-2, or simply the opposite. So the bands related to the vegetation part, plus the spatial latent launch coordinates, because there are some sampling algorithms that they do just the geography. And then the sampling unit. For this exercise, I'm just going to present only the pixel base. Our pixel 100 by 100 meters, because this is the regional protocol, where they do bulk 5 randomly taken samples. And later on, in the coming future, we will also test the other unit. So it's not intra-pixel, but it's really 5 composite samples within a field. So one field is 1 lab data. And then, for today, I'm just going to present the application of the smart sampling tools at the population level, so the project level, but in case we want to see also if it's an added value to apply a different strata that we can have on a project or even on a farm. Because even on a farm, like this one, we have just 200 hectares, just 1 block. Or the same, another opposite situation where we have a farm that needs to be sampled, but we have scattered plots everywhere in the landscape. So basically then we start the iterative cycle. So we have tested 5 sampling algorithms from the simple random sampling, stratified k-mean sampling, stratified key medoid sampling, conditional latent hypercube sampling, and geography. Part of them are known, part of them are less known, and then we iteratively apply from 0 to 100% of the pixel that we can sample. So from 0 to 706 samples. Applying many, many iterations to get the uncertainty. And we measure, this is a kind of results of the accuracy metrics. So we compute this kind of metrics. So the Jensen-Shannon divergence, the Kolmogorov-Smirnov distance and the filter space coverage, and the marginal efficiency that was already mentioned before, and of course the uncertainty in terms of coefficient of variation for the different sampling strategy across the density. So from 0 samples to 706 samples. So this is 100% of our sampling density. To understand where we have the elbows, where is the best numbers to retrieve and make a decision. Then we create a framework of multi-criteria decision analysis score, taking into account not just the uncertainty, but also the cost and the accuracy. We vary the weights because, of course, we cannot have always the same relative importance of the weights and the cost. So we apply it, and we got a kind of MCDA ranking for the best combination of sampling strategy, sampling unit, density, to really see which is the best according to our landscape, taking into account also the sensitivity of the different weights that everybody here in the room can apply, because someone can give more weights to cost, someone else like the scientist, more to the accuracy, probably the bias to the uncertainty. So we want also to understand which is the importance of varying the weights to get the same stable answer all over the exercise. And then we got the summary. I don't know why we... you can go back to the presentation. Thank you. Puoi tornare, Carlo, gentilmente alla presentazione. Okay. I don't know. So we can... Okay. So I'm going to present briefly some of the metrics to understand, for example, which is the best strategy. So we have here on the right the different sampling strategy, and then we will analyze the first metric, so the Jensen-Shannon divergence. So basically here, every time we can calculate this value, that is a matrix that tells you how different is your sample population compared to the full reference population. So if we do sample like 10%, okay, 70 samples, compared to the 706 samples, the statistical distribution, how they differ to each other, okay? So basically, the objective is to get the zero identical distribution, but of course, it's technically impossible because it's too costly. So this is the zone where we have the elbow of the curve, where we can understand something about the efficiency of the different smart sampling algorithm. And this is one of the cases. For example, you already see that the stratified k-means at a certain time already at 10%, 7.5%, already gives you a better, lower JSD. But what about covering all the maximum error? Because we can have, on some part of the landscape, some error between the sample population and the full reference population. And this is given by the Kolmogorov-Smirnov distance that answers this kind of question. What is the biggest gap or all in our data representation? And again, the objective here is minimize the maximum divergence. And in fact, you see that CLHS, together with k-medoids and stratify, already always minimize the maximum gap between the different sample and full reference population. And again, super important when we do deal with big extension, with many, many phases across the space coverage. So did we visit when we identify like 70 samples, or every type of soil and vegetation combination, because these are the information of our multidimensionality landscape, because we are talking about the predictor that our remote sensing variables bands. So of course, one is the total coverage of the feature space. And you see again that we have two candidates, stratified k-means and k-medoids, that really address the real variability on the field. And then last but not least, the marginal efficiency. So we need to identify the elbow where return diminished. So every additional sample that we do add, which is the impact on the cost, and especially on the decrease of the accuracy. What point does the spending more money stop giving us new info? And of course, again, this is the zone and the sampling algorithm that help us really to minimize. So at a certain point, we doesn't need to add 10 or 20 samples because it's too costly. We do not add any kind of insatable information. And then what about, I want to create some complexity, and what about the different contribution of the different predictor that we use from satellite? Just vegetation can be used, and you see this is an application of the different sampling strategy, and each point you get the best sampling strategy with the lowest JSD value, and you see that there are more or less the same type of curve, but can also be used where, of course, we do not have always bare soil. The answer is partially yes, but if you do have bare soil, it's better to mix both. So the vegetation bands from the Sentinel-2 and also the bare soil bands. And you see, again, around the 10, 15, 20% of the sampling intensity, we have, again, two candidates that can be considered the best sampling strategy. But then we apply the multi-criteria decision cost. So we apply, for example, in this kind of exercise, different weights, 40, 30, 30, for accuracy, uncertainty, and cost. And for the different predictors, vegetation, bare soils, and spatial with also latent launch, and all the remote sensing bands, you do see that the highest MCDA score means the best combination of accuracy, uncertainty, and cost with a fixed weight. And you see that stratified K-means most of the times is one of the candidates. But then when we start varying the weights from 0 to 100% of the different, accuracy, uncertainty, and cost, this is the most interesting part. So you got the top 5 ranking on the most table. So it means that we do not select one strategy, combination of sampling algorithm, predictors, and intensity that works perform only well for one parameter, but is performing well in all the 3 parameters, even if we do vary the weights. And this is the stratified K-means is the winner. So for our landscape, for our conditions, we decide to, and this is a representation of the effect of the sensitivity. So you do vary the weights of accuracy, you do vary the weights of uncertainty, and for different, this is an exercise made for 10% of sampling intensity, always, most of the times, stratified K-means, and the second position, the K-medoids, is the winner. So we apply the stratified K-means, and this is the situation. We're lucky that thanks to the 71 points, so this is a sampling intensity of 1 sample every 10 hectares, we do represent well our full statistical distribution with low accuracy and the lowest cost. We got these samples around. So we visit basically every part of the farm with good reasonable numbers, especially for the operators that they have to travel and organize their travel. Just 37% of the fields have been sampled, theoretically, because in reality we sample everywhere. So then we upscale, so we apply within the strata, because we have identified 71 strata, to all the fields that have been not sampled. And we got the clay and the soil organic carbon, because you can imagine these are the 2 input variables for our ROTC modeling over these surfaces. And then we also got the bias. In general, we can say that even if we do not apply any statistical regression or any machine learning predictors, because we could also apply it, because we can train and validate with all this data and say, okay, we take 71s and we apply a spatial machine learning prediction algorithm to predict the soil organic carbon. But this is the most simple upscaling exercise, so that we upscale in the strata, and we got perform, you see, an absolute bias for soil organic carbon that is quite reasonable, acceptable. But the most important, we do not under-credit or over-credit potentially, because we will see at the end of the 5 years crediting program, but we fully cover the real statistical distribution. So in blue, you have the observed one, the statistical distribution of the 71 samples, so 10% of the 706 samples. So this is the estimated one. Sorry, the opposite. The same for root mean square error, so we do not have big extreme, unless the farmer they didn't tell you that they spread the digestate. And of course, the labs tells you that you got more carbon than the satellites, of course. That's normal in our area, but I think everywhere. And the same for clay. That is, again, is reasonable well to apply this kind of stratified K-mean strategy on our condition. So my last take-home message, this is our quad and auto sampler that we normally use. The key message is start sampling, not geography, but variability. And I think this is a kind of exercise that can be applied also somewhere else, but for us it was super important because sampling less but smarter means really reduce a lot the MRV cost. And in general, the net margin for all the players when we do certifying and issues the credits is possible only if you add this kind of variability or data-driven approaches that can really help you to make a smarter decision. Thank you so much.
Maybe we have time for one question, very fast one. Okay. Maybe I don't see any question. Maybe I can ask one first one, Andrea. How do you see the applicability of the methodology on the selection in an area where you don't have the full measurements and you are coming in and then you don't want to pay and then say, okay, I could have reduced the cost?
Yeah, I think we can easily upscale because if you apply this data set and use these predictors to your data set, I think, of course, we know that the mineralogy is different, the reflectance of different type of soil can change. But again, the answer is you go randomly. So at least you can get, probably you don't get if you apply directly on the predictor. So you apply this strategy using just the predictors, not a validated spatial models to predict soil organic carbon. Of course, then you measure and you use the measured data. But I think the alternative is that you go randomly. So you stratify using agronomical data, soil types, but you never know. So unless you don't have some already existing data set with which you can somehow do this kind of exercise. And I think if we leverage the agricarbon data set, our data set, the Luca data set, many other data sets are there, we can really come up with a standardized methodologies and to say, okay, look, this is your uncertainty, because you can also create uncertainty values when you do apply, even on just on the predictors, because I think there are many data there that can be used to really validate this kind. And if it's not stratified, okay, can be K-Medoy CLHS, that is very well known, but at least you are sure that at least 80% of your statistical distribution of your predictor is taken into account. Probably some tails are not taken. Probably there you do not run your models. You just use the delta shock for the plots begin to these groups, just like this. To me, is doable.
Okay. Thank you. So we go to the next presentation. I think it's Simon from Chris Lab. Maybe he will present himself also.
All right, hi everyone. I'm Simon. I'm a researcher at Chris Labs. And today I'd like to begin by thanking the organizers for giving us the opportunity to discuss the topic of our session, which is the cost accuracy bottleneck that the industry is currently facing. And that bottleneck is a reflection of, on one hand, the rigor imposed by proper carbon protocols and the associated expenses. And on the other hand, you have the economic viability that project developers face. And today I'll discuss how at Chrysa Labs we are leveraging in-situ sensing and data-driven optimized sampling to tackle this issue. But before I go into the details, I'd just like to give you a quick overview of what we're doing at Chrysa Labs at the moment. So we have a talented team of over 40 scientists software engineers, technicians, and project specialists that are actively working on carbon. We have pulled over 400,000 soil cores, for which we have both lab analysis and paired probe data. And we have done this over 2 million hectares across 10 different countries. And this has allowed us to deliver de-risked carbon quantification. And the way we achieve this is through this chain, where we typically begin a project using smart sampling design, where we will partition the surface area into zones where we think that the SOC will evolve in a similar manner. This reduces your measurement variance. And then we'll conduct a financial study where we will explore the sensitivity of the economic burden that the project developer will face as a function of sampling density. And once we pick a sampling density, we will move on with the field sampling, where we have a hybrid strategy, where we combine a strategic fraction of lab samples and in situ sensing, which has lower costs because you don't need to ship soil to the lab and analyze it. And then we'll move on with our predictive modeling, where we will map raw spectroscopic data to actual carbon stock, and then move on with proper quantification. So now back to the topic of our session, which is this bottleneck that project developers face, and it's a trade-off between the cost associated with high-density sampling and the anticipated uncertainty, which is not always easy to predict. So the approach we took at CRCF Labs is, instead of having a static view of this problem, we explore the symbiotic relationship between three pillars. On one hand, at the moment, we have a very high-quality, high-density data sets consisting of 60,000 sampling locations over 200,000 hectares. This allows us to, in retrospection, simulate various scenarios. And then we can use this massive ground truth data set to optimize the stratification that we are currently developing. And then the top two green tiles on the slide help us refine the inputs of our financial optimization engine. And these inputs consist of the anticipated measurement variance and some financial parameters that we can put in. And what this model spits out essentially is an optimized sampling density that helps you better strategize and de-risk future projects, and then we can add more data, and then you see the pattern here. It's a bit of a rinse and repeat feedback loop so that we can become better at it. All right, so now I'll jump into a little bit more details about each of these three tiles that I just showed. The first one being this simulation, where we use real data from 60 sampling locations, where we have this large area for which we have these gray dots, which represent sampling locations for which we have both ground truth data and probe data. And then you can do three things with this data set. The first one being reducing the area of the project and see how that affects your anticipated uncertainty. And you can also play with two other parameters. The first one is the one on the x-axis here, where we vary the probe substitution ratio and see how our performance is evolving. And then the y-axis here is we just, with the red dots, just remove a sampling location to simulate sparse sampling. And the cartoon on the left-hand side, the quantitative result is the one on the right-hand side, where we vary sampling density and we look at the resulting uncertainty deduction. The different colors represent different project areas, and as expected, when you aggregate more stratified data together, you improve the certainty of your outcomes. And the solid line represents the status quo scenario, where you do 100% lab data, whereas the dashed lines represent a scenario where you would reduce the lab analysis by 50%. Of course, the penalty you pay is your model error, which adds to the uncertainty according to the Vera VM42 methodology. But as I'll show later, that's not a problem. Because of the reduced costs, we can reach higher sampling densities with the probe and recover that penalty. And then the shaded region is just 95% of your outcomes in the Monte Carlo framework that we're using. Now, moving on to stratification, what we do is a bit simpler than what Andrea presented, but it would be nice to discuss after. But we essentially start with open data layers, such as soil texture or topography, and then we combine that with land use history to define these homogeneous zones where we think the carbon will evolve in a similar manner. And then we put random samples in each of these strata, and we can use either SOC predictions or the data from our data set to validate that our stratification is working well. And then we need to pick a sampling density, and this is where the financial considerations come into play. We'll also take into account fields, roads or rivers, things like that, to facilitate the work of the samplers. So now the financial considerations that are tied to sampling density are the following. We will assume a carbon price. This allows you to put a price tag on your uncertainty deduction. We'll consider some sampling costs and project scale. And a cartoon version of what this entails is this graph here, where we vary sampling density and look at the economic burden, which is the sum of your sampling costs, including lab analysis costs, plus the price tag on the uncertainty deduction. And the orange curve represents the scenario where you would do 100% lab. Of course, the uncertainty is a bit lower, but the lab costs scale faster than the CRCF lab cost as you increase sampling density. And what this allows us to achieve is this optimal point here, where we reach a higher sampling density with lower upfront costs and lower uncertainty deduction. The quantitative version of this graph is the following slide, where we have built this parameter space where we can explore any project. The x-axis on the left-hand side here is the sampling density, and the y-axis is the project area. And each pixel on this graph represents a possible project. And the color of that pixel is the economic burden that I defined on the previous slide, which is your upfront cost plus the expected uncertainty deduction cost. And the goal of this parameter space is to find this valley of profitability, which is this straight line on this log scale, which corresponds to the minima of all these contour curves. Now, what happens when you consider a scenario where you reduce the lab by 50% and you reduce your upfront costs? We see that the valley of profitability moves towards the right, so we can reach a higher sampling density and recover that uncertainty penalty while maintaining a similar economic burden or an even lower one. So with that, I'd like to conclude by saying that we've developed a financial optimization engine that is data-driven. This allows you to de-risk your project. And in the future, I'd like to refine this feedback loop with more temporal data, in particular for paired sampling, where you go back at your remeasurement at the same spot. I would like to see how the temporal correlation evolves with time. Perhaps it's better to sample every year rather than waiting 3 years. Yes, and before I finish, I would just like to acknowledge that this has been teamwork. In particular, Clémence, a young, talented data scientist at CRCF Labs, has helped with some of the coding behind what I showed today. Gabriel Manja, who's our co-founder and CTO, supervised a lot of this work. John is an intuitive scientist that helped bridge the gap between those simulations and the stratification algorithms that Damien and Rigel, both physicists like me, we all studied together, have been working on. And I'd just like to highlight the poster that Laurence will be presenting. She's here at the conference. And if you have any questions, don't hesitate to come see us or contact us. Thank you.
Thank you, Simon. You can answer in this microphone. Yeah, we have time for 2 questions, or yeah.
First, thanks. I was curious, is your optimization algorithm basically working in the entire world, or is it focused in the US? Because I saw that most of your data points are coming from the US currently.
Yeah, that's a very good question. That's a good question. At the moment, it is optimized for the US, but we believe we can extend those results to new region as long as we compare the ground truth data we have from the US to data that we have to find from Europe. The other thing is the possibility of SOC distribution, it's log normal, there's known bounds. So there's not that many scenarios we can't simulate. As long as we put a proper range of possibilities for the project developer, we could say, look, we're not certain of the SOC distribution in advance, but if you pick those sampling densities, here's the range of outcomes or economic burden you could face. Now let's find the best solution together. But you are right, at the moment it's optimized for North America. And Latin America, we have a lot of data there too.
Do you have another question? Yeah. We will go to the next presentation, and then during the discussion session, maybe we have more of these interactions. So I think we covered all the presentation, right? Yeah, we did, indeed. So now we head to the second part of the session. Maybe we can go to the first slide of the first presentation, first slide of the session, and I leave.
There's no presentation for this pitch. You're all right. So if I can just invite the panelists down, and I'll introduce myself while they're coming down. My name is Stuart G, and I work for Climate Kick. I kind of lead our work in Ireland. Just grab a seat wherever. And I am not a data scientist, so I will admit that some of that went way over my head. What we work on in Ireland is very much, just grab a seat anywhere, guys. Just grab a seat there. Come on. And so what we work on in Ireland is very much around trying to close the gap between current reality and climate ambition. And we have a partnership with the Department of Agriculture for the last 4 years. So we're very much looking at systems innovation and how innovations can get scaled to help us close that gap. So that's why I'm here, and why the topic of the panel discussion is supposed to be around barriers to systemic barriers to scaling some of these innovations. I'm going to let Guillaume introduce himself because he hasn't been speaking yet. The rest you've already met, so I'm just going to let Guillaume introduce himself first.
Yep, so thanks a lot for the invitation and thanks for the organization. So I'm Guillaume, I'm the head of solution engineering at MyZFarm. And basically to introduce MyZFarm, we are a tech company, we are a software provider. We have a clear mission, which is to support the transition toward more sustainable agriculture by providing digital solutions to make it credible, measurable, and scalable. So yeah, today we provide digital solution, or let's say a digital backbone, for different types of programs, both in-setting and off-setting programs. So we work with food industries, cooperatives, to help them on basically the MRV solution, but also with project developers. We work with French project developers using the label bas carbone. We work with a project developer using the M42 internationally or gold standard. So always helping them with the digital platform which support them in this type of programs. We cover today, I think, about 25 countries where we digitized about 30,000 farms and more than 1 million hectares. Yeah, and basically today I will discuss more in detail, but we are using the technology presented by Ahmad and the technology of the CSB as part of our MRV workflow. So yeah, happy to discuss later about this.
Thank you, thank you. So look, I suppose I said the topic of the discussion is around the systemic barriers to scaling some of the innovations that we've been hearing about. And I was kind of trying to frame how would we get into this, and I think actually Helena put up a lovely slide at the start, and I think one of the other guys put up this more or less the same slide. There's innovations along, like, let's call it the value chain for measuring soil carbon, all the way along it. And how do we, is there nearly too much innovation that it's hard to figure out which one is the right one to scale? Maybe it was one of the questions that was coming into my head. But I'm going to just throw it open to the panel. What are the barriers to scaling some of these innovations? So where do you think the barriers to getting them utilized more? you know, when we talked about carbon farming this morning, it's the age-old one. How much are we going to get paid? So the incentive, the cost incentive is the big one, or the price incentive. Here we're talking about reducing costs significantly by what I can gather from across them. So that's not the barrier. So how do we get these things scaled? Or is there a barrier? Are these things being scaled? I'm going to throw it to Andres to start.
Yeah, thank you. I mean, as I said, also try to answer to Ahmad. I mean, the technology is there. The data-driven approaches are already years and years that are there. I think, as I show you, I mean, our example is just a very small example, but there are many, many other big examples like Crystal Labs or AgriCarbon. I think we need to be sure when we scale up that the technology works. I mean, when we have a region, when we have the data, this region is enough to say that our technology is scalable, because when we talk a lot here in this Congress about scalability, to me it's not just moving from one field to another field. We need to embrace the concept of a project. A project is a big, I mean, depending on which is the supply chain, but also the supply chain or an offsetting project. So we need to be sure when we propagate the error that this error comes from exercise that at a certain scale are true. So we have to prove that in a kind of scale why we have chosen this 700 or 1,000 hectare scale, because this is the likely size of a carbon farming project in our area. So we cannot say that easily when we scale up to 1,000 hectares on another southern region of Italy, it might work. So we have to be very careful on selling that this is scalable, because this hampers the ex ante, because as a farmer wants to be enrolled and embrace the journey of carbon farming, whatever is the incentives, whatever are the risks that are taking, when you present to them a number, baseline, first of all, versus carbon farming practices, our model needs to be calibrated for those carbon farming practices, because not all the models are able to simulate those carbon farming practices. Because behind the delta shock, there is a value. Cost of implementation, 70% of the gain, because 30% is kept under buffer. And if these numbers does not come from projects or models that are really calibrated for your model domain, all the system fails, to me, because they is going to take the risk. And if you do not ensure to them that 70% of the likely gain, of course, we have an extreme events, of course, we cannot handle this. But at least our model should always say, is calibrated, and this is the likely uncertainty. Because with uncertainty, I mean, you can manage and you take the best decision.
Okay, thank you. Does anybody else want to come in on that one?
I can add a quick thing. Yeah, for us, with the acquisition rhythm we have at the moment, there's about 10,000 samples coming in every week. And something we have to keep in mind is we presented some nice statistical stuff today, but sometimes we have bigger fish to fry, which is cleaning up the data. Of course, when you have 80 people at any given time in the field, there will be issues, there will be logistical issues. Sometimes the data we receive, the masses we measure, don't make sense. You also have to worry about losing some soil from your core, because when you measure grams of carbon in a soil core, you have to propagate it to a surface area. If you get the diameter of your tool wrong, not by measuring it with a ruler, I mean the effective diameter when it penetrates the soil, if you get that wrong, you introduce a huge bias in your reported carbon. So I think the low-level, immediate field sampling issues are a blind side right now, and I think AgriCarbon is doing a good job at this. They seem to have a really nice field machine that I would like to see in action. Yeah, things to keep in mind when you have large-scale projects is some of the samples, you have to discard them, and you need to identify them.
Very good, very good. Go ahead, Helena.
So I see, I'm going to say first thing, we're not cheap enough yet. For commercial environment, it is still too costly to do MRV at scale. So with that, in that landscape, what I think are barriers in relation to technology. I don't think we've yet found the sweet spot in terms of combining ground truth measurement with modelling, with remote sensing, to ensure that we have confidence in applying those as a suite. That's where we need to get to make this cost effective at scale. And as I've said before, I do think one of the missing critical bits of data is this delta SOC in relation to regenerative farming practices and not having to use literature-based values that reflect individual management practices. Until we have that, I may be wrong, but I just don't see how we're going to drive down that uncertainty and therefore reduce the cost. And that, to me, is a critical part of this jigsaw. Now, it doesn't seem to say we can't do it. We've just started resampling. Told you agricarbon started in 2020, first sample in 2021. Resampling, oh my God, we thought stock data were bad to handle. Stock change data are really fun. But that's the sort of data we now need to start getting to grip of to really, I think, fundamentally drive the change. And within a few years, we'll have really good data to be able to do that. So I try not to be disheartened. We're getting there. We've made massive leaps. Final point. I still think there's massive technological engineering solutions out there. 80% of the cost in sampling is getting the sample. It's not the lab analysis. I didn't emphasize that enough. Dare I say drones? Let's think out the box here. What is the best way to go about it? Is it robotics? Is it automation? We've really got to think out the box here to make this easy, quicker, and more reliable.
Go ahead.
On my side, I just basically not adding something new, just wanted to illustrate on our side with our use case, which is not directly to soil organic carbon, but indirectly, let's say, with cover crop biomass. And basically taking a very concrete example, because we work with cooperatives. I will take an example in the west of France. There is 100 farmers, and basically after doing, let's say, a carbon farming program, they clearly identify that the main lever to increase the amount of soil organic carbon in the soil is to produce more biomass, mainly thanks to the cover crops. So they have a concrete in-setting program with one of their clients, and within this contract, then they even have to justify the increase of biomass cover crop biomass with a specific thresholds, like 1.5 or 2 or 3, I don't remember, but they have to justify it. And they need a scalable solution for this specific data point, which indeed will be used later for modeling soil organic carbon, but still they need to prove and measure on a scalable way the cover crop biomass. So that's why we are working with the CSB on their technology in this specific context. But if we take the example of, and basically what we need to do is to have ground truth data, and to basically illustrate your point, when it comes to cover crop biomass, and when you want to use a remote sensing approach, you need data which is specialized, because you need to make it, let's say, make the link with the pixel of the satellite. You need a very specific protocol, and basically, at least on a farmer point of view or cooperative point of view, no one is doing it, except in very specific programs. And we don't have any ground truth data, or very limited number of ground truth data. And we have to, for each project, basically put it in place and find a way to find this measurement. So it's great. Cover crops is a good way to improve the biomass and the carbon. But farmers are doing more and more complex mix of cover crops with different species. So we need more and more measurements, more and more ground truth data. And basically, there's still a gap in this part to really be able to scale.
Go on, if not.
Yeah, thank you very much, Guillaume. Actually, my comment was going to be the same as you, so I will just try to combine a little bit on what we have. I heard from each of the experts here. So challenges, this was a question. There's challenges on the ground to get the measurement, to making sure the quality, to making sure that the methodology is cost effective, scaling up, maybe looking further. And then how to analyze the data or process the data or produce information like what Andrea was mentioning, what I presented. But actually, then you get the challenge of the, which is actually would be the first one that you need to address, is what are the needs? We should start with the needs. And this is where Guillaume said, okay, I have my clients, this is the case. So my sentiment that I hear of it is that right now, there is a big challenge in the insetting value chain, inside the value chain actually exercises. If you are making measure to measure over 5 years, and then the value chain is on one of the production in the value chain, you need to make estimate over 1 cycle, 1 year, like measure, remeasure, you will not do it. So then, okay, you measure, remeasure, and then you try to find the contributions, or you make modeling and try to find the contributions. But this is 90% of the market in the US. This is not the case in Australia, okay? But in Australia, one of the projects is 45% of all the voluntary carbon market. One project is 45%. So we cannot use all these statistics. But in Europe, and I know in France, this is a major point. So we need actually to go through these challenges in an iterative way. And I think that inside this, everyone mentioned data accessibility. So it's always there. This is the insetting exercise, Guillaume, and on the ground and all this stuff. So
you're beating me to my next question.
This was a great one. Great question, thank you.
Very good. You're beating me to my next question, because it did come up in a couple of the presentations. Like and this is a challenge we face in Ireland, because we have loads of data, not necessarily on soil carbon, but on lots of other things. But data access and data interoperability, and platforms where people can put their data so it can be used to build better models and all the rest. We see that as a significant challenge in Ireland, because you have all these legacy projects and initiatives, and the government contracts one person to do soil samples, and then 5 years later they change to someone else, and they don't share the information and all this stuff. So to put that back to the panel, what can we do? Have you come across an innovation or a data platform or some kind of sharing system through your work that could make that possible, or that more people could kind of replicate and do? Does anybody want to take that on? Or if you haven't seen one, what would it look like? Go on, Helena, go on.
No, I saw he had his hand up.
Did somebody have an answer for that?
Yeah. Go for it.
We want to get it interactive.
Public involved.
There's a few regional observatories that provide all sorts of data that we need to evaluate MRV tools. There are a bunch of them. One on which Andrea is working in northern Italy. There's one, the Regional Space Observatory in southwest France, that we have developed in 2002, and similar one in Finland. A few lighthouse farms also. The point is that we are currently there is not a lot. There is a lot of data, but there is not a lot of useful data to evaluate MRV tools that are not adapted to the kind of exercise that we want to do in an operational context. So apart from those observatories that contain different sorts of measurements, soil measure, above ground biomass, CO2 flux towers for some of them, there is no really adapted observatory network to evaluate MRV tools now. And we had a discussion on that yesterday in one of the sessions. And so we need a clear strategy on building on the current observation networks, like the soil monitoring national soil monitoring networks, that already collect soil data, but don't collect activity data, and don't collect biomass, above ground biomass data. We cannot use them, because if we only see carbon stock changes, but we are not able to say why it's changing, it is because of changes in management or carbon input through biomass, they are useless. So we have to build on them, add some more measurement, and then we have a few more like that we can build on, and they are the high-cost sites that are very few. It's 14 for arable land in total in Europe right now. So that contain all the measurements we need to evaluate MRV2s, but it's too few of them. So it means they are essential, but we have to complete that with other monitoring network. So I was mentioning the National Soil Monitoring Networks, or LUCAS, but there are also those regional observatories, like in Finland, in Italy, in France, that have farm scale measurement that allow to produce the kind of biomass data, for instance, that Guillaume was mentioning. And just to finish on that, in the context of projects like Marvik and CAFAMOR, we are currently building this kind of data set that we need. For instance, for the crop and cover crop biomass, we are building the first EU scale database that will allow us to develop parameterize new algorithms, improve MRV tools, and up to now we didn't have any strategy at EU scale to actually evaluate properly, improve, develop those MRV tools. So we have to think about it a bit more seriously now.
Okay, thank you very much. Just something comes to my mind there. So when you guys collect data from farmers, or you get the soil carbon data, who owns it?
Depends who pays for it. But in reality, there's a lot of negotiation has to go on in terms between the farmers and the projects that are actually implemented on the ground. So there's no one single answer to that. But I'll give you the example of what happens at AgriCarbon. So AgriCarbon has a use license, which is a license of relationship between whoever's effectively funding or managing, project developing it, the farmers involved, and AgriCarbon, which enables the use of data to improve the marketplace, and that's quite generic. So we have quite a lot of working relationships with research organisations, working with the data to analyse it, etc. And that is upfront. And customers, clients, and farmers are allowed to say no, they don't want their data as part of that data set. So it's held separately, it has no access rights, it's purely privately owned. But the vast majority of the data that we hold is held almost like in custodianship for all of the people that have generated it. And interestingly, it has rarely been an issue about who owns the data. Now that might change as we start to see results coming from projects, and we're aware of that, but also beware, it's very regionalised, so I suspect that Simon might have a different experience from US in terms of data ownership, where there's much more, there's a different perspective.
Yeah, my understanding is that the growers on our side own the data, but we have a perpetual license to use it. But I'd have to confirm with my boss, because he's the one that talks to the lawyers. I just analyze the data, but that's the gist of it.
Yeah, just wanting to complement on the fact that maybe the data ownership is still not yet an issue. I not fully agree on that, and at MyZ Farm we have a very different position. Like we even have a label from the Farmer Association in France, because all the data we basically have more or less in our infrastructure is owned by the farmers, because at the end it's coming from their fields, from their farm, and so on. And typically, when we take the example of our use case here, where it comes to cover crop biomass, this collecting organisms, which are basically at the end valuing their supply chain to their clients, they see a lot of value being the ones able to provide a really precise, carbon farming emission factor of the crops, and basically being, it's really a competitive advantage to have such technology and being able to be better than the others in terms of reporting. So today, when we launch like private project when it comes to cover crop biomass, I can tell you there is no way we basically benefit from this cover crop biomass for other clients. They are really owned by the farmers and by the cooperatives. So yeah, just wanted to complement.
One second, just before you come in. I know we're just up on time, people, so if anybody is starving, please feel free to walk out. We won't take too much longer. Go ahead, Andre.
Now, coming back beyond the ownership of the data, is about how the value data chain works. Because from my side, I mean, I'm taking the cap of a researcher, we have already always talked about plot scale, small scale experiment. And now we face the problem that we cannot scale up some, super detailed solution. From the other side, from the company and farmer or supply chain sides, the spatial extent and the quality of the data, how they have been acquired, doesn't work for MRV. Because since we're talking about soil carbon removal, and we all know that except some farmers, they do really good job in terms of sequestering tons of carbon. But the majority of farmers is like, looking for a needle in a haystack, because we are talking about really low signal of change. And if we do not have the primary data, activity data, really able to say, okay, in this particular combination of soil, practices, climate, and many other adds-on, we cannot. And we cannot even scale up. Because if we do acquire data at academia, at plot scale, in experimental farms, we cannot scale up. We can scale down from the data that we are acquiring from the industry. I mean, we were talking before with my colleagues. I was asking him, how is it going, the calibration of our light use efficiency model to estimate crop yield using tons of data from the agricultural consortium? It doesn't work because they just provided 10 fields and an average data. But within the fields, we have a huge distribution of data of biomass. And if we do not have access to this data because they have never been acquired in a way that can fit for our purposes, scalability, validation, and calibration, it doesn't work. So the uncertainty will always remain such high, and we cannot say that it's credible, the number that we're providing.
Okay, maybe to wrap up this part of the conversation, I think maybe there's, I don't know, I'm just thinking out loud, but maybe there's an opportunity here with the CRCF registries that if schemes or projects are accredited and they've used accredited methodologies, that data could sit there and it could be potentially accessible to other projects to build better models and stuff. I don't know, just thinking. And maybe on the, the principle for me, I'm a farmer's son, so I'm going to say this obviously. I know from talking to my brothers and friends who are farmers, they want to own this. They want to get a value from it. Now, whether that's a big value or it's just give me €5 to access the data, but that across thousands of farmers adds up and it goes back into reinvested in the agri sector. Like there's lots of things in Ireland where there's a levy on the price of meat that goes back to the farming organisations, all these little things, but they all help, and people at least they feel there's value to it. So just think maybe as a principle going forward, it's something that maybe we should consider. I'm going to open to the floor for a couple of questions before we finish up. If anybody has any questions, I won't take it as a slur if there are no questions. So you'll just say you're hungry. There's one over here.
Thanks to you all. I was just wondering, but maybe it's too early, I don't know. So you have been talking about uncertainty, etc. But so for the CRCF, resampling has to be done every 5 years. So I wonder, in your opinion, is that feasible to detect the change?
Watch this space. But the only thing I'll say was, I would have said originally, I didn't think so. I probably say now I think I'm changing my mind, but it's early days. But by the end of this year, we will hopefully have sampled around about 100 farms. So we should have a better idea. I'm optimistic is what I'm going to say, but there's a lot of noise.
Everybody else nodding their head or agree or disagree?
Yeah, I agree. And the one thing I'll add, and then I'll let everyone go eat, is with the right sampling density, then after 5 years, yes, you should be able to detect a carbon change. And there's a direct link between the uncertainty deduction that we showed today and the minimal detectable difference. Just need to pick statistical significance and the power of your t-test, and as long as it matches what you expect, you should be able to detect that change. I'll end here.
So it's about the level of investment in the sampling, essentially. Anybody else? One final question before we finish up? Oh, got one here.
Thank you. When you talk about costs, I assume you talk about total costs of MRV. And how does it look like if you think in terms of fixed costs versus variable costs? And is there any studies or struggle to bring the fixed costs a bit down so that the smaller scale are also feasible?
Very, very good question. I don't have a simple answer for that yet because the fixed costs are so high and therefore are detrimental to smaller scale projects, definitely. I think the methodology within the CRCF might open a window there because in all honesty, I'm probably going to get shot down. There are routes to be less stringent within that might better suit some of the smaller projects. But at the moment, what we're seeing is smaller projects have to combine to make it cost effective. And that tends to be the way at the moment. I wish I had an easy solution for that one.
Yeah, there is obviously the soil organic carbon related cost with stratification, sampling design, going to the field, taking the samples and so on. I think there are some costs also related to the digital infrastructure, softwares, because at some point you need to be able to collect data from the farms related to the practices. In some countries it's very easy, in some countries you start from nothing, so you have basically to have someone, or at least being able to put in front of the farmer an interface to be able to collect this information, like the, I don't know, tillage practices, fertilizer application, things like this. At some point you need to get it. So these are MRV costs that can really depend on the country, really depend on the situation of the project, really depend on the supply chain, because simple example, I take the example of France, all the cooperatives, grain, cereals, they all have a farm management system. They all collect data for regulatory purposes. They all have a lot of data, let's say, available. If you take example of sugar beet industry, they collect only one crop, they don't have any farm management system, nothing. So you start from nothing. So you need to put in place the whole digital infrastructure when you want to start a regional ag or, let's say, carbon farming program. So definitely the cost will be quite different in these two aspects. It's just one part of the cost. So there is a lot of different, I think, initial costs that we could discuss.
Just to add on that, I mean, the fixed costs are still high, of course. You can decrease if you aggregate because it matters a lot. But even if you decrease, fixed costs, variable costs for MRV, even if you implement the best smart data acquisition strategy, digitalization, it's all about the real delta SOC that the farmer can achieve applying only real well-done practices. Because if we're talking about just, again, finding a needle in a haystack, because we just apply a few times a cover crops, not well done, sowing late, terminated early, we are really trying to find something for a solution that is like a change of 0.0 percentage of soil organic carbon. So how can we handle this? I mean, MRV can be scalable, yes. We can decrease the cost thanks to the technology. But if the first input is not a huge delta SOC changes that makes it economically viable for the farmer and for the project developer, we're talking about nothing, honestly. Because if you really do have just one cover crops as the only practices over 5 years, or two cover crops over 5 years, even sounds minimum tillage, we're talking about 0.something tons per hectare per year. Even if we decrease at 4 euros per hectare at the cost of MRV, which is the net gain for someone? There isn't.
Okay, on that optimistic note, I think, look, just to sum up, I think this is one of the things we come up with in Ireland all the time, because like soil carbon is expensive to measure accurately. It's why I think, and I think a lot of the conversations this week are around what's beyond carbon. And obviously in Irish context, we're very keen to get livestock included in the CRCF, because that's where most of our emissions lie. But I think the other conversation I was having yesterday was we need to incentivize innovation in soil management so that in 50 or 100 years we have healthy soils that will be productive and resilient to the climate that we have at that time. And I think while it is expensive, maybe the recommendation here is, or maybe the insight is, this is a public good, and states need to step up and make sure that it's going to get cheaper. We know it's going to get cheaper, but states need to step up to have good data sets that we can build models off of going forward. I know, Ahmed, you wanted to come in, but I think we're a bit late. So I'm going to stop there and thank all the panelists for their time. Ahmed is available for questions and that. Everybody's available for questions over lunch if anybody wants to chat. Thank you very much. Did you want to finish up, Ahmed?